Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatro from the Department of Physics and Astrophysics, University of Delhi, India. Today we are going to talk on the module Energy Dispersive X-ray Spectroscopy of the topic Surface Morphology, coming under the paper Characterization Techniques for Materials 2. After completing this module, the students will be able to understand what X-ray generation is, about the Moseley's law, and the basic components of the EDS system. Energy dispersive X-ray spectroscopy, generally abbreviated as EDS, is an analytical technique used for elemental analysis or chemical characterization of materials. Each element in the periodic table has unique atomic structures and allow set of characteristic signals in the electromagnetic emission spectrum. Capturing the signals with respect to the variation in energy is the concept and fundamental principle of spectroscopy. In EDS, the interaction of X-ray excitation source with the sample is monitored by measuring the emission characteristics of X-rays ejected from a specimen after stimulating with a focused X-ray beam. At rest, an atom within the sample material contains ground state electrons in discrete energy levels, or electrons stay in cells bound to the nucleus. The incident beam excites an electron of the inner cell and ejecting it from the cell while creating a hole on the same place. An electron from the outer or the higher energy level fills the hole by releasing energy in the form of an X-ray radiation of amount equivalent to energy difference between the higher and lower cells. The counts of the X-rays emitted from the specimen in the energy spectrum is scanned and measured using the EDS spectroscopy. As the energies of the emitted X-rays contain information of the difference in energy between two cells and atomic structure of the emitting element, the EDS provides estimation for the elemental composition in the specimen. Let us learn about the X-ray generation processes. The inelastic interaction of the electron beam within the specimen atoms produces two types of X-rays in the scanning electron microscopy system, and peaks in the energy spectrum appears. These are characteristic X-rays and continuum X-rays. In the first category, the characteristic X-rays are produced when electrons from the incident beam eject inner cell electrons from the specimen. The characteristic X-rays are identified as peaks on a background of continuum X-rays. The second type is continuum X-rays. These are produced when the electrons of the incident beam interact with nucleus of the specimen atoms. Figure 1 indicates the EDS spectra for the characteristics and continuum X-rays. The production of characteristics X-rays. The electrons of the incident high energy beam, denoted as E0, create a hole in the inner shell of the specimen atom, loses the energy E by transferring it to the ejected electron. An electron from the outer shell subsequently fills this hole in the inner shell. The energy difference between the inner shell electron and the outer shell electron is emitted as a characteristics X-ray quantum as shown in figure 2. Let us study about the continuum X-rays production, how it develops. The continuum X-rays represent the background on which the characteristics X-ray peaks appear. A high value of peak to background ratio is essential for proper identification of elements using the observed characteristic X-ray peaks. Interaction of the incident electrons with the Coulomb or electrical field of the atomic nuclei leads to loss of energy from electrons in the beam that produce continuum X-rays. The distribution of this energy loss is continuous and not a characteristic feature of the atomic number of elements in the specimen. The closer the beam electron comes towards the nucleus of the specimen atom, the stronger is the interaction with the Coulomb field of the atomic nuclei, and more energy is lost by the electrons of the beam, and correspondingly more energetic X-ray photons are emitted. The difference between the actual and observed intensities of X-ray emission spectra may occur due to absorption by the window of the detector that allows the emitted X-rays to pass through for detection. The intensity of the continuum background increases with probe current, atomic number, and accelerating voltage. Characteristic X-ray nomenclatures. The X-ray lines are named using a capital Roman letter indicating the cell containing the inner vacancy K, L, M or N with a Greek letter to specify the group corresponding to the line, that is alpha, beta, etc., and a number to denote the intensity of the line within the group, that is 1, 2, 3, etc. The characteristic X-ray lines are nomenclatured in accordance with the cell where the vacancy is created by the ejected electrons and the cell from which an electron migrates to fill the vacancy created in the inner shell. The schematic of the characteristic X-ray lines are represented in figure 3. For example, if the initial vacancy occurs in the case cell and the vacancy of the filling electron migrates from the adjacent cell L the X-ray is said to be emission of K alpha line. If the electron migrates from the M cell to cell away, the emitted X-ray is a K beta ray. Similarly, if an L cell electron is ejected and an electron from the M cell fills the vacancy, L alpha radiation will be emitted. Within a given cell, there are electrons in orbitals differing in energy due to bonding effects and gives variable intensities. The K alpha peak comprises of the K alpha 1 and K alpha 2 X-rays that appears very closely and unresolved in the EDS system and termed as K alpha 1 2 doublet. It appears as the K alpha peak at an energy between the two individual components and an intensity corresponding to the weighted average of both the K alpha 1 and K alpha 2. The most probable transition occurs between the adjacent energy cells, as when a K cell vacancy is created, the transition from L to K is the most probable one. Hence, K alpha radiation process greater intensity than K beta radiation, as the energy difference between the M and K cells is greater than the energy difference between L and K cells for K alpha radiation. K beta radiation appears at higher energy compared to the K alpha radiation while progressing outward from the nucleus. The energy difference between the adjacent electron cells decrease, and hence the energy released upon electron transitions between adjacent outer cells is less than the released for adjacent inner cell transitions. Hence, for a given atom, the energy trend for the radiations is as follows. The M alpha radiation is less than L alpha radiation is less than K alpha radiation. Spatial resolution. As we studied in lecture 1 of scanning electron microscope, the inelastic interactions produce diverge effects including secondary electrons, phonon excitation, cathodoluminescence, which is in visible light fluorescence, continuum radiation, and characteristic X-ray radiations. Also, it produces plasmons and Auger electron production by ejection of outer cell electrons. The X-rays are produced from deeper side of the interaction volume formed in the specimen as compared to the secondary and backscattered electrons. The backscattered electrons originate from interaction volume more closely approximating that of X-rays, and therefore they are a useful imaging signal to correlate with the X-ray analysis. In fact, the backscattered electron signal is the signal of choice for correction with X-ray maps. X-ray spatial resolution depends on the specimen's density and overvoltage. The following equation shows a good estimate of X-ray interaction with the sample, and the equation is R is equal to 0.064 multiplied by E0 to the power 1.6 minus EC to the power 1.5 divided by rho, where R is the spatial resolution in micrometer, E0 is the accelerating voltage in kiloelectron volt, EC is the critical excitation energy in kiloelectron volt, and rho is the mean specimen density in gram per cc. The Moseley's law. The energies of the characteristic radiation for a given series of lines vary monotonically with the atomic number Z and is given by the Moseley's law as E is equal to C1 times Z minus C2 square, where E is the energy of the emission line for a given X-ray series, that is K alpha, Z is the atomic number of the emitter, and C1 and C2 are constants. Moseley's law is the basis for elemental analysis. With the energy of a given K, L or M line, the atomic number of the element producing that line can be determined. The X-rays of K, L and M series are having increased energy values for higher atomic number elements as shown in figure 4. Within the normal accelerating voltage range from 15 to 20 kiloelectron volt used for EDS analysis, the lightweight elements emit X-rays of the K series only. The intermediate weighing elements emits X-rays of the L series or K and L series. The heavy elements emit X-rays of the M series or L and M series. The basic components of EDS system. The EDS system detects the X-rays ejected out from the sample specimen. The schematic of the EDS system is shown in figure. The absorption of an individual X-ray photon by the detector leads to the production of a photoelectron that utilizes its energy to form electron hole pairs in a single crystal, and subsequent formation of charge pulse with exposure to the external electric field. The charge pulse is converted to a voltage pulse by passing through a preamplifier. The generated voltage pulse is proportional to the energy of the incoming X-ray photon. The signal is further amplified and shaped by a linear amplifier called pulse processor and passed onto a multi-channel analyzer, where the data is displayed as a histogram of intensity versus voltage. The main components of EDS system includes an X-ray detector that detects and converts the X-ray into electronic signals, a pulse processor which measures the electronic signals to determine the energy of each X-ray detected, and a multi-channel analyzer which displays and interprets the X-ray data. The X-ray detector. The EDS detector is a self-contained vacuum system called a cryostat with cryogenic pumping created by liquid nitrogen cooling or alternative methods such as Peltier cooling. The basic components of X-ray detectors are schematized in figure 6 and includes the collimator assembly, electron trap, cryostat and electronic attachments. First, the collimator assembly. The collimator provides a limiting aperture through which the X-rays pass through to reach the detector, ensuring that only the X-rays from the limited area being excited by the electron beam are detected. Second, the electron trap. Electrons that enters the detector cause background artifacts. The electron trap is a pair of permanent magnets that strongly deflect any passing electrons that could cause background artifacts. Third, the window. The window helps maintaining vacuum by isolating the detector crystal from the chamber of the microscope while being as transparent as possible to low energy X-rays. Earlier, windows were composed of beryllium, which did not allow low energy X-rays, that is less than 0.9 kiloelectron volt, to pass through it. However, modern windows are composed of polymers and allows low energy X-rays down to around 0.1 kiloelectron volt to pass. Fourth component is the crystal. The main material used for crystal is silicon, and lithium is added to compensate small levels of impurities. When an incident X-ray strikes the detector crystal, its energy is absorbed by series of ionizations within the semiconductor, and a number of electron-hole pairs are generated. The energy of the incoming X-ray is dissipated by the creation of a series of electron-hole pairs in the semiconductor crystal. The electrons excited to the conduction band of the semiconductor are free to move within the crystal lattice. The excited electron leaves behind a hole which behaves like a free positive charge within the crystal lattice. Under an applied bias between electrical contacts on the front and back of the crystal, the electrons and holes sweeps to the opposite electrodes, producing a charge signal. The size of the signal or the voltage step is directly proportional to the energy of the incident X-ray. The fifth component is a field effect transistor. The field effect transistor is the primary step of the amplification process that measures the charge produced in the crystal by an incident X-ray and converts it to a voltage output. During operation, charge is built up on the feedback capacitor. The sharp steps on the voltage build-up, as shown in figure 8, are due to the charge created by each X-ray event. The voltage step size is proportional to the incident X-ray energy. This accumulating charge should be periodically restored to prevent saturation of the preamplifier. Sixth is the crosstalk. The charge signals generated by the detector are small and can only be separated from the electronic noise of the detector if the noise is minimized by cooling the crystal and FET. The noise determines the resolution of a detector, particularly at low energies. Generally, the full width half maxima of an X-ray peak is of the order of 2 to 10 electron volt. The actual FWHM is at least an order magnitude greater than this due to noise in the system. The EDS detector is cooled using a continuous filling of liquid nitrogen held in a devar. The vacuum is maintained at a level low enough to prevent the condensation of molecules on the crystal. The pulse processor, the signal, that is the voltage step from the preamplifier, is transformed into a voltage pulse that is suitable for the multi-channel analyzer. Shaping and noise reduction of the signal are achieved by digital computation. The noise on the voltage ramp from the detector is effectively filtered out by averaging this signal. The time over which the waveform is averaged is called the process time, is denoted by Tp, and can be controlled by the operator. The longer the Tp, the lower is the noise on the voltage ramp. If noise is minimized, the resolution of the peak in the spectrum improves and can be easily separated or resolved from another peak that is close in energy. However, there is a trade-off between the process time and the speed of measuring the data. The longer the process time, the more time is taken to measure each X-ray, and fewer are the events that can be measured. Productivity in the detector depends on the rate of counts measured, called the output count or the acquisition rate, rather than the input count rate. However, at very low count rates, the output and input counts are proportional. As the input rate increases, the acquisition rate also increases, but larger number of events are rejected because they arrive in a short time period than the processing time. This phenomenon is termed as pulse pileup. If input rates increase sufficiently, the proportion rejected will exceed the increase in measured events, and the acquisition rate will start to decrease with further increases in input rate. This situation is most dramatic for the longer process time. Now let us study about the multi-channel analyzer, abbreviated as MCA. The MCA takes the data from the pulse processor and displays it as a histogram of intensity or number of counts versus voltage. The voltage range displayed on the x-axis is divided into a number either 1024 or 2048, etc. of channels, each corresponding to a given energy range, for example 5280 to 5300 electron volt. The MCA takes the peak height of each voltage pulse, converts it into digital value and puts it into the appropriate channel. Thus, a count is registered at that energy level. So students, let's summarize what we have learned in this module. An EDS spectrum is essentially a histogram of the number of X-rays measured at each energy. In the EDS system, the energy of the incoming X-ray is dissipated by the creation of a series of electron-hole pairs in the semiconductor crystal. The electron-hole pairs are swept away by an applied bias to form a charged pulse, which is further converted to a voltage pulse by a preamplifier. The signal is further amplified and shaped by a linear amplifier or a pulse processor and passed onto a multi-channel analyzer, where the data is displayed as a histogram of intensity versus voltage. Thank you.